We're live. Okay. So, LeetCode on a Fluke. We picked I picked a random problem at medium level. I'm trying to share it. Hope it's looks like it's being shared. And I have no idea what this is about, but I see that there is a number of, okay, we need a number of substrings with only ones, okay? Given a binary string S, return the number of substrings with all characters ones. Since the answer may be too long, return it modulo. Okay, I've seen that already. So that means we need to return the remainder, basically the last, well, it's, yeah, the last numbers after dividing, the remainder after dividing the answer by this billion plus 7. I don't know why. I don't remember why plus 7, but okay, so given so the length of the binary string is from 1 to 10 to the power of 5. Oh, I forgot to restart the. Anyways, we have 2 minutes in. We're 2 minutes into. And it's either 1, 0, or 1. Return the number of substrings with all characters 1. Okay, what does that mean? So what is a substring? So there are 5 of length 1, okay. There are 3 of length 2. And there are, oh yeah, there is 1 of length 3. It looks like there is a dynamic programming solution here. Could be helpful here. Okay, input is 101, so output is 1. Explanation. Hi. Explanation. Substring 1 is noun. Is shown 2 times. Yeah. So this one is 6 ones, and 6 ones have. So the dynamic programming, I mean, it's kind of so we know the solution for 1, it's 1. When the solution for 2 includes what? It includes the solutions, so for 1 2 times. And the solution for 3, so it includes, solution of length. So it has this one time, and plus, yeah, I should put like that, I guess. Or so that substring 1 time plus the solutions for 2 solutions for that. So 3, on the other hand, has one solution for 3 ones. Then it has yeah, and we can probably, yeah, once we've done 2, we know what 2 has. So 2 has 3, right? Right. But 3 has 1 plus it has 2 different substrings of length 2 plus it has three substrings of length 1. I'm just thinking that there is an overlap in terms of this length 1 substrings. This one counts them also. So we just need to factor that in somehow. But otherwise, if we factor that, let's look at this as a sub problem. But overall, that's one way to do it. One way to do it. And so 3 in that case will have what? It's like 3, 2, 1. So it's 6. 6. Okay, so 3 has 6 in it, and that 2 has 3 in it. That's why we get 9 here. We have a 2 and we have a 3. But each of these already include the shorter substrings factored in. But to get a solution, so I mean, let's do one simple. Let's get one simple idea. We can store the solutions for shorter for sub problems, and that way we don't have to recalculate them again. Okay, so have a dynamic programming, some kind of slice, some kind of data structure to store them. Another way to look at it is, because it's a binary string, it could be something like a binary tree here, some kind of binary calculation, because so binary calculation For example, this says 6. In binary, that's in binary numerical system, it's 1, that's 2. And the third digit is 4. These are 4s, these are 2s, and these are 1s. So that would be 7 in a binary calculation. That would be 3. That would be 1. But in our substrings, that's 6, so it doesn't match in our substrings, right? Because these are 2 to the point 2 to 0 to the power of 0. This is 1. This is 4. Yeah. So, what if it's like 4 1s? What happens there? Well, then, if it's 4 1s, we have then 2 3s. Okay. 2 3s. Yeah, let's start. Let's just, 1. We have 1 of that length. We have 2 3s. We have 2 3s, yeah. How many 2s do we have? 1, 2, 3. It seems to me there is still a pattern. I mean, that we can calculate the number of combinations. Threes, and there is 4 1s. Yeah, so there is a math. So that is 4 1s. Yeah. So that is 1, 2, 3. So 6 plus 4, that's 10. So 4. And basically, it looks like a progression. So if we go, we see 1, 1. If we see another 1, we can calculate that number. Basically, yeah. It looks like we could. Yeah, and let's just do to make sure. Let's do, and by the way, we could do it a little bit differently, like that, to see it's a bit more graphically. So there will be 1 of length 5. There will be logically 2 of length 4, and so on. So it doesn't, I don't see it's requiring us to store stuff, because we already know. If we go over it and we see 1, if you see a 1, and we know how many combinations that is. If we see another 1, we add 2 more combinations, and so forth. We just add more combinations. So we'll have our answer. Answer starting with 0. Yeah, so the rest, So there will be 2 4s, and there will be basically there will be three of these, I guess 4 of these, and 5 of these, yeah. So that will be 10 plus 5 is 15. And then we'll add 6, and that's why, yeah. So now that, I think we figured out the pattern. So if we go over for that value, arranging our string, if that value, if v is 1, so we just need to know if we are still in the sequence of ones, and like in substring is false initially. And yeah, we'll be tracking if we're starting over, or we can just say current sum, and let's disregard that maximum for that sub-problem. Let's just do the basic. Let's say we are within the boundaries of integers. So, and then we'll address that other problem. Current sum is 0 also. And if current sum is 0, then we're starting new. Yeah, and if it's, yeah, we'll figure that out now. So we don't, if it's 0, then it's a different story. Yeah. And we need to return answer. Current sub, that's how, yeah, our substring sum. No, yes, current sum is this number of substrings, number of substrings in this current substring. So yeah, if we see a 1, there are 2 cases. If we already have some if current sum, there is a case when current sum is 0, and there is a case when it's not 0. So we have something going on already. And we need to know, by the way, how much we have going on. Count as 0. We'll count how many we have currently. So if it's 0, if we hit a 0, if the value is not 1, so we say that counts, we reset the count as 0, the current sum is 0. If we have a 1 and we have something and by the way, if we have a 1, yeah, we need to say count plus. So we need to count it. All right. Now, and that will be our first one. Let's say if it's our first one, if current sum is already has something, yeah, so there is we counted, or I mean, we can use count or current sum for that matter. It doesn't matter. So we have something going on. Or if count is actually what we need to do, because based on our logic, if it's the first value, we just need to add 1. Do we really need to? Because I think we can just do current sum plus count. Because yeah, if it's 1, we add 1. If it's the second one, we add this 2, and we accumulate those. We don't need, we might be fine with that. So yeah, if it's 1, we add 1. If count is 2, we add 2 to the current sum. And yeah, what's our timing? 21 minutes. Yeah, and and that's our current sum. And if it's if we have a 0, then we say answer. We add the current sum to the answer, and then we reset them. And that should be working for our test cases. Output, no, it's not working. Answer. So why? So it shows 3 expected 9. Okay, we're getting some. Why could it not? What's wrong? If we have a 1, we add it to the count. We add the count to current sum, so it's 1. If we have a 2, if at that moment, let's say if the next value, so okay, let's try that test case. We have a 0. We're pretty much we're going to the next one. So we get a 1. Count is 1 now. And then current sum is 1. We have another 1. So count is 2 now. Current sum is 3. We have a 0. Answer gets, oh yeah, that last one. Okay, yeah. So that last flush, yeah. So if current sum, or basically we just need to add, we just need to add answer plus current sum. Yeah. This last one, yay, our test cases. Okay, we solved the little numbers. But what if we get an integer overflow at the current sum level? Because the current, if we get a lot of these, and it could be all ones, like 100,000 of ones. So, but we only need those current sums. Yeah, so we add the count. So if current sum is, I mean, we could just remainder divided by 10 to the power of 9 plus 7 each time. So that would give us our number until it gets, when they're equal, it will get us a 0, and when it's 1 bigger than that number, we'll get us a 1. Yeah, and it will be growing after that timing, and it will keep us only the remainder. Oh, it will cancel all the full number values of full amounts of that. It will clean our current sums, but then that might be enough. Oh, there is no yeah, so value of type in, oh sorry, yeah, so that case didn't work for some reason. Why would that be? Why would it return 1? So we only cut the longer part. I mean, it never got into the 1,000,000,007. We never got to the 1,000,000,007. I don't understand why. What we're saying here is we want just the remainder. So if we hit that billion sum amount, then cancel it, or like billion sum, but that's 10 to the power of 9. I'm sorry, I don't think that it works like that. I think that in Go, I think that in Go it's different. Yeah, I think that, yeah. So that it's not a exponent in Go. It's a bitwise operator. Yeah, that thing. That's why. Yeah, bitwise operator. It's a different operator, basically. Yeah, not exponential, right? Yeah. Anyway, so 28 minutes, and we're close, I think. But I mean, let's say we got this billion, and we have like 100 of billions collecting. So it never gets to the 1,000,007,000. So it gets only to the to that. So we do want to optimize that value as well. And by the way, we probably can't do it like that now. It should be working. So that thing we also need to use for our answer. Because, yeah, let's say we'll add the billion to our answer. Now we need to update the answer as well. So optimize answer as well. Oops. Yeah. Let's give it a test. Let's give it a test. Okay, can we do it in oh no, okay, one test case. Wrong answer. Wrong answer. Okay, use test case. It looks like a lengthy test case. Let's see. Okay, we're close to almost all of the test cases, but let's see if we can fix that within like the next few minutes. So our answer is bigger. And the question is the problem in how we reduce and how we do this modulo? Is that the problem? Because I think if we try to do that, we'll run out of time. No, we're not running out of time. Let's remove and try and see. Oh, so we had so we isolated that operation. We were fine. Yeah, the output is not something too crazy. We just got a wrong answer. Yeah, the answer is not too big. It's just a wrong answer. Let's try to fix that. So what could be wrong here? Because at the end, it shows it was a bit bigger. Now, what could be wrong? We flush when we hit a 0 or when we are out of the string. So if that last substring was at the very end. But that's when we flush it to the answer. And that makes sense. If v is 0 or if we are at the end, if v is 0 or we are at the end, so we flush and we return the answer. I feel confident we're close because we passed so many test cases. So count is 0. We reset the count and we reset the current sum. And oh, by the way, it looks like that thing is pretty long. Looks like that thing, I don't know how long it is, but it does generate this. This is what, by the way, how big is that? 200 million. Yeah, 200 million. Okay, so 33 minutes. We have this little bug somewhere. Hopefully it's a little bug, yeah. Answer is starts with 0. Current sum is 0. Count is 0. Okay, if we see a 1, we count 1. and we add it to this current sum. If we see then we see a second, and okay, and the third, and that's how we get 6. Okay, and then we have a 0, and as we go through zeros, we add the current sum is 0, so we reset the count and the current sum, but we don't really change the answer because the current sum is 0. And I don't think that operation also changes anything. So through zeros, we just pass, basically, ready to find another 1. And when we find another 1, we start, count 1, and we add it again to the current sum. Then we hit another 0 here. We flush the 0 to our answer. And that's what happens with all the 1s here. 1 0 1 0 1, then the 4, then yeah. So I think it's pretty straightforward. Could something go wrong in the bigger values? That's a question. On bigger values, could something go wrong? And I mean, we're still within our integers. Yeah, int 30, yeah, 32-bit integer is 2 billion. Yeah, we're very safe, right? Wrong. Well, our answer, oh, so our answer jumps out of that. Oh, my goodness. I think I see a little problem here. Oh, gosh. Oh, gosh. Oh, gee. Oh, sorry. Oh, gosh. Wrong button. Gee. I have an idea. No. I mean, this remainder thing might not be working as I'm. I need to test this. What this looks like. I need to test this in a playground and see what it looks like. So let's say it's like, let's say it's 3. I want to see what it's. So 3 actually gives you 4 zeros. Oh gosh. So we need 8. Yeah. A little miscalculation. Yeah. That's hardcore. Yeah. Within 40 minutes we solved it. Yeah. So that's just how we generated that billion. Yeah. So we have 1 0 here. Then we add those exponentially. Yeah. Those 8 zeros. Yeah. Solved. Yeah. So medium level problem solved in linear time. Is it linear time? It is linear time. Yeah. In linear time, within 40 minutes, and I think it's good. I think, yeah, I like it. I like it so far, and it looks nice and clean. Thank you for watching. Like and subscribe. Like and subscribe. We'll see you in the next video.